Hello, I'm going to be doing my presentation on cryptographically secure pseudo-random number generators. Now, random numbers are very important in cybersecurity in all sorts of applications. Like when you're generating a key for a cryptographic algorithm, then you need to have a random number generator in order to generate a key. You also need random number generator in order to generate a nonce for various purposes. That being said, Ed, the random number generator you use can be quite important because if you use a weak random number generator, then an attacker could use what's called a random number generator attack. They can figure out which generator you're using, reverse engineer it, and then figure out what random number was generated. That now Now, generating truly random numbers often requires special hardware that can be impractical to implement for most purposes. So, computers will often use what are called pseudo-random number generators. These are algorithms that generate sequences of numbers that look like they're random, although they actually aren't because most computers cannot generate true randomness. Now, most traditional pseudo-random number generators are unsuitable for cryptographic purposes. They're too easy to reverse engineer. They can be, and an attacker, when given enough outputs, can figure out how the parameters of the random number generator, like the seed and whatnot. And based on those parameters, they can, just based on a few outputs, they can figure out what all the outputs of that generator have to have been. Working backwards to figure out past outputs, and also working forwards to figure out what any future outputs of that generator will be. Here's an example of how a traditional pseudo-random number generator could be reverse engineered. This is the linear congruential generator, or LCG. It's a very common pseudo-random number generator. And the way it works is to get the next output, you take the previous output, multiply it by A, and then add B, and then take mod M. So for our example, let's suppose that our LCG is generating 4-bit outputs. This is quite small, but we are doing a bit of a toy example here. So M in our case is 16 because 4 bits can only go from 0 to 15. Now, suppose that with our LCG, we observe that an LCG outputs 10, then 9, then 4. We can plug those into the equations you see on the right, and then just subtracting the second equation from the first, you get 5 equals A mod 16, or in other words, A equals 5. You can now plug in A equals 5 in either of these equations and figure out that B equals 7. So now, and with that, we now have the parameters of this linear congruential generator, and we can use those to figure out that the output that it made before 10 was 7, and after 4, its next output will be 11. And we can keep going like this, figuring out what all of its outputs are going to be. Now, when it comes to traditional pseudo-random number generators, one that has been proven to be secure is Blum Blum Shub, or BBS. It's named after its authors, L. Blum, M. Blum, and M. Shub in 1986. And the way it works is you choose two primes, P and Q, that are both 3 more than a multiple of 4, and then you find N is the product of P and Q. Then you choose some initial value X naught, and for each output, you take the previous output, you square it, and then you take mod N. And and the thing is, for security reasons, you have to only output the last bit of the output. With large N, you can output more bits, but outputting only the last bit is always secure. The number of bits you can securely output is proportional to log N. Now, Blum Blum Shub is secure because it has Blum Blum and Shub proved that in order to figure out the parameters given the outputs, you have to factor n. And of course, this is just like RSA, whose security also comes from the difficulty of factoring large numbers. So accordingly, to use Blum-Blum-Shub properly, you should be using really, really large P and Q. And there are some number theory tricks you can do to choose initial parameters such that the cycle length, the number of outputs before it starts repeating, is very long. So here's an example of Blum-Blum-Shub. We're going to use some fairly small primes, p equals 103 and q equals 107. And this gives us n equals 11,021. And I've arbitrarily chosen the initial value to be 37. So for the first step, we take 37 squared, and that is 1369. That is odd, so we output a 1. Then for the next output, we take 1369 squared, and when we do that, mod 11,021, we get 591, which is also odd, so we output a 1. Then for the next one, we do 591 squared mod 11,021, and that gives us 7630. This is even, so we output a 0. And we continue like this. So in this case, we get the output 1100111111. The, and I did run this out further, and it turns out with these primes and this initial value, the outputs end up repeating after every 104 cycles. Of course, with large primes, you're going to get a cycle length much, much, much longer than that. Now, this is great and all, but then comes the problem. How do you actually generate the parameters for Blum-Blum-Shub securely? You need to get them from somewhere. You can't use another Blum-Blum-Shub because then you need to seed that one. So this creates a problem of how do you determine a seed for a pseudo-random number generator? Most of the commonly used seeding methods are insecure. Like using the current time is a pretty common one, but that's a problem because if the attacker knows even approximately when you started generating random numbers, then they have a pretty small number of seeds to check. Like if they know to the minute when you started generating, then even if you're seeding to the nanosecond, that's only 60 billion seeds, which may sound like a lot, but it's not that much to a particularly dedicated attacker. And of course, it's also much, much less than the number of possible seeds. Also, using your username as the seed is also obviously insecure, since an attacker could easily find that out. Using another pseudo-random number generator to seed, well, that creates the problem of how do you seed that pseudo-random number generator, and that can also and using another random number generator to seed a random number generator can create a phenomenon called RNG jitter, which can actually make the outputs less random. So we want to avoid that. So this creates the question, how do we seed a random number generator securely? Our one solution comes from the cryptographically secure pseudo-random number generator in Unix called /dev/random. /dev/random is based on an entropy pool. Essentially, the operating system tracks hardware interrupts. It uses the time differences between interrupts in order to generate entropy or randomness, basically, and then insert it into an entropy pool. The entropy pool keeps track of how much entropy or unpredictability it has accumulated. And then you can read bits from /dev/random. This will decrease the amount of accumulated entropy. And if you try to read too many bits compared to the amount of entropy that the entropy pool has generated, then the program will block until enough entropy has been generated. Now, Z. Gutterman and others analyzed how /dev/random worked in Linux in 2004. And in that system, in that version of /dev/random is initialized using a combination of OS parameters and external entropy. And the entropy pools are updated using what's called a twisted generalized feedback shift register, and which is used because it has a really, really, really long cycle length before it starts to repeat. And bits are extracted from these entropy pools not directly, but instead they're transformed using a variant of SHA-1. Now, Gutterman and the other authors found that found a few vulnerabilities in this implementation of slash dev slash random. While most Linux distros will write a seed file during shutdown, which it can then read again during startup in order to basically have the random number generator pick up where it left off, some distros don't do this and will instead just initialize the random number generator from scratch on every root reboot, and which drastically reduces the number of potential states it could be in. Also, they found that they ran an experiment where they let a Linux computer idle for 10 days, and they found that it had accumulated 17,500 bits of entropy, which isn't that much. If you're using art slash dev slash random a lot, especially if an attacker is using it a lot, this makes it very vulnerable to denial of service attacks. Here we can see a visualization of how the al slash dev slash random and slash dev slash u random, which doesn't block when it doesn't have enough bits, operates. The system takes various hardware interrupts as sources of entropy, and it adds them to a set of three entropy pools. Slash dev slash random will try to draw entropy from a secondary entropy pool if possible. If that, oh, if that, and entropy will be added to the second entropy pool if possible. If entropy is added and the secondary pool is full, then it will be added to the primary pool. If bits are requested from a secondary pool and it's empty, then bits will be taken from the primary entropy pool. Here we can see the algorithms in pseudocode that Linux uses to add bits to the entropy pool on the left, and you can see there's a lot of XOR operations. G is the actual entropy that's being added to the pool, and it gets transformed in various ways before being added. And then on the right, we can see the algorithm that Linux uses to extract bits from the pool. So you can see how it uses some variants of SHA-1 to get 160 bits from the pool and transform them. And then those 160 bits get folded, XORed in various ways to produce 80 bits of output. Nowadays, Mac OS uses an algorithm called Fortuna for its slash dev slash random. Fortuna uses a block cipher to generate bytes. Specifically, it uses a block cipher in counter mode with a 256-bit key and a 128-bit counter. So basically, it encrypts 0 using a random key, then it encrypts 1 using a random key, and the outputs of these are used as random numbers. And thing is, every time bits are requested from Fortuna, it will generate an output as usual. Then it will generate another output, which will be used as the key to generate the next output. This ensures that past outputs are secure because it means that the system doesn't have any memory of what keys were used in previous outputs. Also, the generator is periodically reseeded using a set of 32 entropy pools. And these pools are used in an alternating pattern where the 2 to the ith pool is used in every ith reseed. So it'll use the first pool, then the second pool, then first, then third, then first, then second, then first, then fourth, and so on. And this ends up being enough pools that it effectively ensures that virtually all future outputs are secure since a system will virtually never be running for long enough to need the 30-second pool to reseed. Here we can see the algorithms that Fortuna uses. We can see how it uses SHA-256 to generate a new key when needed for reseeding. And, and we can see how it uses the block cipher to generate pseudo-random data. It only allows you to generate up to 2 megabytes because a block cipher in counter mode will never generate the same block multiple times. But truly random data will occasionally generate the same block multiple times. So an output size limit is implemented to basically hide the fact that it's pseudo-random. Now, L. Dorendorf and others, a similar team to who analyzed the Linux CSPRNG, also analyzed the Windows CSPRNG. At the time, this was based on 8 RC4 stream ciphers, which were used in round robin fashion. So like one of them would be used to output 20 bytes, then the next one would be used to output 20 bytes, and so on until they used all 8. Then they go back to the first. And after each RC4 has generated 16,384 bytes of output, then a new key will be generated for them based on 3,584 bytes of entropy accumulated from various sources. And crucially, every process has maintains its own CSPRNG state. The, this me Now Dorendorf and the others found that this CSPRNG had basically the opposite problem of the Linux CSPRNG. So /dev/random had the problem of denial of service attacks because it generated entropy too slowly. The problem with this RNG is that it barely uses entropy. It takes so many outputs before each rekey that they estimate that the ciphers only end up getting rekeyed like every few days. And they found that it's quite easy for an attacker to figure out the current state because unlike the Linux CSPRNG, which runs in kernel mode, the Windows CSPRNG runs in user mode, which makes its state easier to access. And they found that an attacker who figures out the RNG state can pretty easily figure out what all past outputs and all future outputs will be. Hmm. Here we can see the algorithms used by the Windows CSPRNG called CryptGenRandom. Hmm. And, and it maintains variables called R and state. And, and there's a variation of SHA-1 that's used. And there, and we can also see how RC4 is used to generate 20 bytes at a time, and it's only refreshed after every 16 kilobytes of output. Now, much more recently, a white paper was published on how the Windows 10 CSPRNG works, and it's very similar to Fortuna. It generates bits using AES 256 in counter mode. However, unlike Fortuna, the Windows CSPRNG has a buffer that's 128 bytes long, and when only a few bits are requested, then it can just draw from the buffer and only refill it when it's needed. The, and the and also Windows 10, much like the earlier Crypt Gen Random, Windows 10 maintains a lot of CSPRNG states. Not only does it maintain one for the kernel and one per process, it also has, for each of those processes, it also has one state per processor, so that in order to allow more efficient generation of random numbers. Now, all of these CSPRNG states are reseeded according to a schedule. The first reseed occurs after 1 second, then after 3 seconds, then after 9, then after 27, and so on, up to a limit of 1 hour between reseeds. And if any given CSPRNG finds that it is out of date, then it'll reseed based on CSPRNGs below it. So like each process per processor CSPRNG will reseed based on the per process base RNG. And if that's out of date, then it'll reseed based on the root PRNG, which is by definition always considered to be up to date. And once the reseeds reach 1 hour between reseeds, then the number of entropy pools that is used for reseeds will gradually increase. And and the way these entropy pools are used is quite similar to Fortuna, where it uses different entropy pools based on what number reseed it is. So there, that's some information about cryptographically secure pseudo-random number generators. I hope you enjoyed.